For this one, we've got a refrigeration system that is shown. It's going to operate at steady state. It's got a coefficient of performance of 5. It gives you the temperature in the kitchen. That would be the surroundings. So it's 23 degrees Celsius. It says it rejects 4.8 kilowatts by heat transfer to the surroundings from these metal coils on the exterior. We want to find power input, and we want to find the lowest theoretical temperature inside the refrigerator. Now again, pay attention to these units. That's kilowatt. Now let's go ahead and let's draw a picture. So I'm going to say this is the hot reservoir right here. So this would be the surroundings in the kitchen. So that's 23 degrees Celsius. We've got the refrigeration cycle going on. Beta here is 5. Now for a refrigeration cycle, we're going to have work going in. We got a power supply, and that's W dot. Then finally, we've got this cold reservoir down here, and this has a temperature, TC. Now from this one, for refrigeration, remember you're going to take the heat from the inside of the refrigerator, which would be our cold reservoir, and then that's going to be our Q dot, and then we're going to basically displace more heat energy into the hot reservoir with Q dot H. Alright, and QH dot, that's going to be 4.8 kilowatts. So that's kind of the scenario. Kitchen surroundings here inside of the refrigerator. Power input. And our coefficient of performance is 5. Now, let's see what we need. We need the power input. We want to find W dot. Well, if you look back at the refrigeration cycle when we were talking about coefficient of performance, which is beta, we have beta equals QC dot over W of the cycle dot. W dot of the cycle is going to be QH dot minus QC dot. Notice these are all the rate terms. What we want to do is we're going to find the power input. So now we're looking for this. If I can find QC dot, then I can find W dot because I know what beta is. Right, so let's use this equation here to find QC dot. So basically forget this middle piece here. Just say beta equals this, and then we'll solve that for QC dot. QC dot then is going to be beta over 1 plus beta times QH dot after do some algebra. Whoops, this is plus. 1 plus beta there on the denominator. Now beta is equal to 5, 1 plus 5 is 6 obviously, and then QH dot, that was given to us. QH dot is 4.8. Alright, so now we got that. Now that gives us a QC dot of 4 kilowatts. Now we're going to take that and we're going to plug it back into this equation right here. So if you solve this equation for W dot, we're going to get QC dot over beta. So we get 4 kilowatts over 5. That's going to give you 0.8 kilowatts. Now that is the power input. Now notice these signs. If you want, these are just giving you the magnitudes essentially. Okay, so because we know for a power input, W dot should be negative, but this is just basically the magnitude. Since we're calling it the power input, that automatically kind of tells us it should be a negative value. So if you want to have the negative value, you can just put the negative on there. But these calculations are going to give you the magnitude. All right. So there's that, and then let's go down here to B. For this one, we want to find the lowest theoretical temperature inside of the refrigerator. We want it to be in kelvins. So the lowest theoretical temperature, that would be like the ideal case scenario. And ideal case would be where we have beta max. So beta max needs to be greater than or equal to beta equal 5. And we know our equation for that would be Tc over Th minus Tc. So that's got to be greater than or equal to 5. Now let's go ahead and solve for Tc because that's what we are looking for. That's the temperature inside of the cold reservoir, which is the area inside the refrigerator. So we'll say Tc is greater than or equal to 5/6 Th. That's what you get after a little algebra. We already know Th. So that'll be 5/6 times 296 Kelvin. That means Tc then is going to be greater than or equal to 246.7 Kelvin. So this is the lowest theoretical temperature that you could have. So this would be the ideal case, meaning you're probably not going to be getting that.